Hello all, we are going to start a new unit on kinetics. We're going to start by talking about collision theory and how collisions result in reactions and products being made. So if we consider the product H2O, water, and the steps it takes to go from its base components of hydrogen and oxygen to water, we need to consider a couple things. First, on our reactant side of an equation, we have a bunch of hydrogen gas molecules and a bunch of oxygen gas molecules. And if you think back to previous lectures in this class, we know that particles in a gaseous state are moving about freely, bouncing around, moving at a relatively quick speed. It's also inevitable that as they're bouncing around their environment, they are colliding into one another. We're going to talk about why that's important in a moment. With these two bouncing around and being combined, they will form water or H2O molecules. How that occurs is really about the collisions that occur between the hydrogen and the oxygen molecules. The parts of the reactant molecules need to come apart. They come apart by these collisions. And it's not just simply that they're colliding, but how they're colliding as well. And we'll talk about that a little bit later. Once they come apart as a result of these collisions, they then need to reassemble into new particles as the products that you see here, right? So as I said, collisions, the only way for particles to break apart is by hitting one another. These collisions need to be hard enough to break apart these bonds so they can reassemble into products. What makes a collision hard, you might be asking? A strong force is really dictated by the mass of the object and the acceleration of that object. Since the mass of these particles are relatively small, we want to increase the acceleration or the speed. In other words, we want to increase the kinetic energy of those particles, so when they collide, that collision results in a greater force, which in turn will result in products being formed. Look at the images here. We have these adorable little kitties moving at a relatively slow pace, colliding into one another. And the only thing that really resulted is maybe a quick little snuggle session between the two. We look to the right, we see we have a lot of mass and a lot of acceleration moving towards that beam there. That obviously will result in a much greater force, which creates a greater impact, as we see here. Oh my goodness. Right. So these particles need to be bouncing about, and they need to be moving with a fairly steady clip, a fairly steady acceleration. If the acceleration is relatively slow, they'll generally just kind of bounce off each other and go off in their merry way. Most often particles that collide, they just repel off one another and they bounce off into the opposite direction. We refer to this as like an elastic collision where objects collide and then just bounce back in the opposite direction. This has to do with the electrons and protons of each individual particle. And we'll talk about that in a little more detail in a moment here. So as we've stated up to this point, fast-moving particles do hit harder. How can we tell molecular speed? Right? So we have slow-moving particles have a lower temperature. High moving particles have a higher temperature. Temperature is a measurement of average kinetic energy. So when we're taking a temperature, we're measuring the heat, we're measuring the kinetic energy of those particles. To increase the heat energy, increases the kinetic energy, which results in collisions that are happening at a higher acceleration. Higher acceleration equals a greater force, which results in a greater instance of reactions actually occurring. So I want us to think about the different phases of reactions and why it might be very rare for two solids to react with each other. Well, up to this point, you should be aware of the behavior of particles in different phases of matter. For example, you should know that solids just kind of vibrate in place. They don't really move. They just vibrate in place and are kind of locked into this, this specific state. Liquids are a bit more fluid. They move around a bit more than solids, not quite as much as gases. They kind of just slide past one another. You could think of a liquid state similar to when you're walking to lunch, when the bell rings getting to lunch, those hallways get pretty crowded and you're just kind of weaving and sliding past one another, maybe colliding with one another, but you're not really causing a lot of damage or having huge collisions, right? And then gaseous states, that's when those particles are really moving at a clip. Generally, when particles are in this gaseous state is when we start to see more reactions occurring. As I've said earlier, fast-moving particles hit harder. Atoms are surrounded by electron clouds. These negatively charged clouds repel each other, just like when you put the same charge of a magnet together, a negative with a negative or a positive with a positive, they will repel each other. So they need to hit hard enough to overcome that repulsion and be attracted to the nucleus in the center, that positive nucleus in the center. Below, you see some images of that repulsion with the electron cloud and the attractive force of the positively charged nucleus. We're going to talk about in a moment that collisions are not the only key component in ensuring reactions take place. They also need to hit at just the right orientation or the right position. So these particles, they're moving at a pretty steady clip, maybe fast enough to overcome the repulsion of their electron clouds. Certain particles of a molecule are reactive while others are not. So, as I said, certain parts may not be very reactive while other parts are very reactive. Particles also need to hit the right way too. They need to ensure that those reactive parts of those particles are the ones that are interacting with the reactive parts of the particle that they collide with. We call this, when particles hit in the correct way or just the right position, we call that correct orientation. Again, that's correct orientation. So here's some examples of ineffective collisions. Particles may be moving at a pretty steady clip, but they're not hitting in just the right way. So they're just repelling or bouncing off one another. Below, we see the effective collision here. That nitrogen hit that oxygen in just the right way, so it created this reaction. It was able to take that oxygen to form these new products. Right. So how do we determine that these particles have enough energy for a reaction to occur? Many of you have already learned about or talked about energy diagrams, so this will just be a brief review on energy diagrams. Energy diagrams show the speed required to break apart chemicals, and we see that by looking at this activation energy here. So on our y-axis, we see an increase of energy, and our x-axis is progress of reaction or time of reaction. And you see, just like if you were to write out a chemical equation, you'd start with your reactants and with your products. And over time, we have our reactants, and then that energy level, that temperature is increasing. And at that peak there, at that transition state, is when those particles are able to start reacting in a way, colliding in a way to break apart and form new products. As products are formed, that energy dissipates. Again, we call this energy that's required for a reaction to occur the activation energy. It's very easy to see on a graph because you'll get this big spike in energy over a relatively short period of time. Again, if we look at it a little bit more closely and a little more slowly, we'll start with our hydrogen and our fluorine atoms. And as we increase that energy to that activation energy, the hydrogen, the diatomic hydrogen and the diatomic fluorine break apart and then reassemble to form hydrofluoric acid as our products. Right? So activation energy is really what breaks those hydrogens and breaks those fluorines apart so that they can reform, reassemble into a new product, hydrofluoric acid. All right.